Hey guys, hey, what's going on everybody? Thomas Domitrovich here. I see we got Jason Doty. Jason, Colombia wasn't too bad. I got to meet Felix Sandoval, which was really good. You know, you meet somebody online, and I've known him since since COVID, since 2020, and finally got to meet him in person. So that was really good. I was very happy to meet him. But yeah, so Bogota wasn't too bad. We had a really good meeting, and Nihad El Sharif was there. We did our safety by design and all that jazz, and so Nihad and I are working on our IEEE paper and adding some examples, and I did an example on a 75 kVA transformer, which I finished, and I submitted that over to Nihad, and we're still going, hey, David Engelhardt in the house. But so I thought I want to do the same thing around a 500 kVA transformer. So that is what this session is all about. So David and crew, hopefully everybody has your calculators, because we are going to be covering some math. We're going to do per unit calculation, and let's get this started. So good to see you, Jason. I know we'll see you in a couple weeks, right? I believe panel 10 is going to be meeting pretty soon. So we are going to be talking about panel 10 stuff. All right, so this is what we're going to do. I'm just doing our one-line diagram. And I'm going to outline my enclosures, and we will dash these. That's an enclosure. This is an enclosure. And this is my transformer, which is also and an enclosure. All right. Looking forward to getting some stuff done. Let's do Eaton footer. This is like one of my first tech talks in a long time. Been very busy, and I got an email from somebody, or somebody made a comment that said, hey, can you get back to doing some technical content? And I figured, well, might as well do that. All right, so this is our diagram. I've got a 500 kVA transformer. We're going to do 480 to 208, and I believe here's what I'm going to do. I am going to do Eaton transformer impedance values. Let's take a look at Eaton's dry type transformers. And I believe I can do a Control F and do a impedance. So the challenge number one in when we lay out a system is coming up with the impedance values. So for a transformer. Now you'll notice so what I'm showing on the screen is the values that Eaton publishes, And you'll typically see a range, a minimum and maximum impedance value. And remember, each of these values will have a plus or minus 10%. We'll work that into our values. But what I'm going to do is try to find a 500 kVA transformer in here somewhere. And we're just gonna, because we're gonna remember, we're just doing math. And here's a 500 kVA. So this is what? This is a typical data for a 480 volt class NEMA TP1 drive transformer. This is an aluminum, probably most cost effective. There's a 500 and the percent impedance. Where's it at? Percent impedance is this column right here. So we've got a 7.2. It's kind of high. I think I said 5.4. That's typically what I see. There's a 6.6. Remember that now you'll notice is this is a 115 degree C rise. This one was 150 degree C rise. This is an 80. Oh, look, 5.4. There we go. We're going to use the 80 degree C rise, NEMA TP1, 500 kVA. There's the 5.4% impedance. So that's where we got the numbers from. So this is going to be a 5.4% Z. And we have to pick, we're going to have to pick, oh man, what the hell? That's conductor 1. This is going to be conductor 2. See, that's what I wanted to do. I wanted a nice arrow. We're going to assume 50,000 amps available fault current at that upstream panel board. And we're going to use a, I don't know, an X to R of 6. Well, and you'll get the feeling for what that means as we go through. All right, so I've got to pick my conductors and my overcurrent. So this is conductor 1. This is OCPD1. Duplicate. And this is OCPD2. All right, so we got to pick our primary and secondary overcurrent devices, and then we'll have to pick our conductor sizes once we pick the overcurrent devices. The first step is we need the full load amps on primary and secondary. So full load amps, we'll do full load amps. Here is 500 kVA divided by the square root of 3 divided by 0.480. And I did this so you guys can see what I'm doing. 500 kVA, 3 square root divide, 0.48 divide, and I get 601.4. So 601.4, I'm going to delete that. 601.4 amps. The full load amps on the secondary is going to be the same equation. Remember, the equation is kVA divided by the square root of 3 and divide that by kV. And that kV will be either primary or secondary. So 500 kVA, 3 square root divide, and then this will be 0.208, 208 volt secondary divide. So full load amps is 1,387.9. All right. So those are my numbers for primary and secondary values. So 601.4, 1,387.9. All right, let's get rid of that equation. Now, for the primary, if I, for the primary overcurrent device, I go to chapter 4. That's article 450. 450 table. Now, so here's what I'm going to do. I am going to pick I'm going to base it on table 450. So I'm going to write my table reference. Table 450.3b. All right, that's what's going to determine my primary and secondary. I'm going to go with 125% on the primary. So if I'm going to do 125% of 601.4, I take 1.25 times 601.4. That is 751.8. Now I could go as high as 250%. So if I do 2.5 times 601.4, that's 1503.5. 1503.5 amps. So that 1,503, that 1,503.5, if I go to table 240.6, table 240.6, 240.6 tells me, remember, I can't go to the next higher, so I can't go to a 2,000 amp feeder breaker at the 250%. I would go down, so that would be a 1,200 amp breaker, which would be the largest on the line side of the 500 kVA transformer. But I'm going to go with this 125%. I'm going to go with the 125% number, which is the 751, and I'm going to throw that in as an 800 amp breaker. So I'm going to say OCPD1 is 800 amps. All right? So I'm saying OCPD1 is 800 amps, and I'm basing that off of the 125%. I can go to the next higher, and that would be primary only protection. So that means is I don't have to follow the rules on the secondary protection. I would pick my secondary protection based upon whatever I'm supplying. But what I'm going to do there is I am going to do 125% on the secondary. I'm going to do my 125% of 1387, which 125 times 1387.9, 1387.9 times, that is 1734.875, 1734.9. So what I'm going to say is I'm going to go with a 2,000 amp panel board on the secondary. All right. Remember, panel boards, I can go up to 2,500 amps on a panel board, but I'm going to use 2,000 amp. So I have a 500 kVA transformer, 800 amp feeder breaker. I have a 2,000 amp panel board that it's supplying, and now I want to pick my conductors. So my conductor 1. So let me do this. I am going to do this. I am going to copy some stuff here. Copy. Paste. I am going to basically, and if you've just joined us, we are calculating the We're picking our primary and secondary overcurrent protective devices. We're going to be picking our primary and secondary conductors next. All right. So 125% is that. I like to do this. I like to organize my my data a little bit. Copy, paste. So what this is giving me is my transformer size. So these are my basic parameters of my transformer. There's my full load amps on the primary, my full load amps on the secondary. Full load amps on the primary and secondary, and then I have my 125%, 250% numbers, what that yields, and then this is going to be a 2000 amp breaker on the secondary. All right, so that gives me my, that basically gives me my numbers for around the transformer. I'm going to need the full load amps for other calculations. I'm going to need the voltages for other calculations and the impedances. And remember, I'm going to do a 1.1 well, when we get there. Anyway, so my basic configuration is this. I'm going to clean this up a bit. Here's what I'm going to do. I am going to copy this now. I am going to copy all of this, Jason. Copy. I'm going to bring this down here, paste. And now I'm going to get rid of that. I am going to get rid of this. I know that's an 800 amp breaker. We know this is 800 amps. We know that this this little guy right there is 2000 amps, right? I just want to clear this up. This is, whoa, 2000 amps. I'm going to shorten this one up. I'm moving some stuff around. Just because I want to make sure that I got enough room for what I need to do. All right, so now I'm going to calculate, I'm not going to calculate, yeah, I am. I'm going to determine conductor 1 and conductor 2. David, we are calculating for a 500 kVA 480 12208. Yes, with 5.4% impedance. Absolutely, David. Thank you very much. Thank you very much. All right, I gotta move some stuff here. Need to make, there we go. Perfect. All right, so conductor 1. Now, what I know about the primary is I have an 800 amp circuit breaker. So conductor 1 has to have an ampacity of 800 amps. So what I am going to do is I am going to go to chapter 3. I'm going to go to article 310. And I'm going to go to 310.16. And I'm going to look at this table. Right, so this table, now, thanks, David. So what I'm going to do with this table is, first I'm going to brighten me up a little bit. So what I'm going to do here, David, is I am going to, I have to pick my conductor. I'm not going to go through the process of feeders like we do in Article 215, because this is a feeder, of calculating with and without temperature, calculating with and without conditions of use, and then determining which is the greater, because I'm already at 125% of full load amps. So I don't have to worry about that. I'm not working off of full load amps. I'm working down from the overcurrent protective device. So what I've got to do is make sure that my conductor has at least 800 amps, and it's a non-continuous. So I got to remember, this is non-continuous. And I had this discussion, and I know I had some people disagree with me, and one individual came up to me and said, hey, Tom, I disagree that I think it's a continuous load. And he said, because transformers are always on, but remember, the definition of a continuous load is maximum current for 4 hours, 3 hours, maximum current for 3 hours. So I'm going to say this is a non-continuous load. So I need 800 amps worth of conductor. And I need to be in the 75 degree C's. I'm going to use copper. Because it's 800 amps, 240.4B. I need to take a look at 240.4B. I thought 800 and above, we couldn't go to the next higher, but 800 amps or less. Oh, so yes, 800 amps or less. Yeah, so 800 amps or less, we could. We could go to the next down. We could step it down. So very good point, David. 310. I'm going to go to 310.16. I'm going to expand this table again. And now 800 amps. So here's what I'm not going to find a single conductor in the 75 degree column that'll get me to 800. So there are multiple ways to skin this cat. I could say I'm going to go with 3/0, and I'm going to do, I'm going to go with a 3/0 conductor. I don't know how to get out of that, but I'm going to go with a 3/0 conductor, and I'm going to go with 4 of those. That gives me my 800. What if I do 175? What if I do 175? So if I did 800 divided by 175, that means I'd have about 5 pairs of 2 watts. So 175 times 4 is 700. You know what I'm going to do, David? I am not going to play that game. Ain't going to do it. 1,000 points of light. I am going to go straight to say my conductor 1 is going to be 4 single conductor 3/0 copper, and I'm going to make it, I don't know. Give me a length. I'm going to put 125 feet in there unless somebody says different. So I'm going with 4 single conductor 3/0. That would be 800 amps worth of conductor on the nose. And I think 3/0 conductor is probably easy to work. Would you agree with the 3/0? And then let me know if it is 125 feet reasonable. I mean, it says we're playing games. We're doing math. So I can make that any length I want to, but I am going to say that is my conductor number 1. All right. For conductor number 2, I need 2,000 amps. So 2,800. Ooh, 2 800s. You want to go with 2 800s. All right, we're going to do it. 2 single conductor 800 MCM copper, 125 feet. David, you got it. 2 sets of 500 CU. 500. Ooh, 2 sets of, I like 500. Yes. 2 single conductor 500s. MCM. Copper. Let me delete this. Move that over. I'm going to delete this. 500 MCM. All right. So 2 single conductor, 2 sets, 500 MCM, copper, 125 feet. And just for everybody's edification, that would be 2 times 380, which is 760 amps. Right? So that's basically what that comes out to. Now, let's pick the 2000 amp. David, tell me, what do you think for 2000? Would you do... So, 2000 amps. 2000 amps. If I did 500s, 380 divide, that's like 6 of them puppies. So what if I did 750s? What if I did 500 MCM? 500 MCM, 2000. 500 MCM is 380 amps. That'd be 6 sets of 5. So I could do 6 single conductor 500 MCM. 420, 2000 divided by 420. I could do 5 single conductor 600 MCM. What would you do, David? This is on the secondary. I'm thinking, you know, one time I picked a conductor that was a little too large, and I had somebody tell me, you try to bend that size conductor. That would be kind of tough. So I'm going to go with the 500s. I'm going to go with this guy. Unless somebody says something different, you know, speak now, forever hold your peace, because we're making some decisions we're going to be doing math on. And I'm using copper. 6 sets of 400. 6 sets of 400. 335. 6 times. Oh, yeah. 6 sets of 400. Yeah. 6 sets out of 400. And we're going to make this 10 foot. Yes. Six sets of 500. I'm going to go with 500 as well. I like 500 better. I think it's more popular of a conductor size. Yep. I'll use 500. 6 sets of 500. You can only buy 1 reel of conductor. I like it. 6 sets of 500 MCM. I'm using 10 feet. All right. And 500 MCM, that's 6 times 380 amps. And that would give me 6 times 380. 2,280 amps of pure fun. All right. All right, so we got 2,280. So we have a system. We have a system. We have conductor 1. We have 550 kiloamps. We have an 800 amp breaker. We have conductor 1, which is 2 single conductor, 500 MCM. Oh, look at that. Yeah, I see what you're saying. 1 reel. Now I get what you're saying. Ross, Eldridge. All right, so we have, and then on the secondary, we have 6 single conductor, 500 MCM, 10 foot, and I have 125 foot. Anybody disagree with the lengths or anything like that? Are we golden? I'm feeling good. And it really doesn't matter, because what we're going to do, the process that we're going to walk through, it will be the same regardless. So if you pick a different conductor, just use different impedance values, but the math will all be the same. And what we're going to do is we're going to next, so now that we have secured the one-line diagram, we are going to create the impedance diagram. And we're going to convert all of the components in here to an impedance. And then we're going to use Ohm's law. But the next step is the impedance diagram. So now I am going to take this one-line diagram. I'm going to do this. I'm going to hit copy and paste. All right. So let's do it. Let's erase this. Let's erase this. Need an eraser. All right. So I am going to draw the one line, the impedance diagram next to this diagram. And I wish this was bigger. Let me unlock this. I don't know if that's going to get me in trouble, but if it does, I'll just keep an eye on it. All right, so here's what we got to do. So the first step, the first thing we have up here is the 50 Ka with an X to R ratio of 6. So what that's going to be represented as is a resistance and an inductance. Okay, so this is, we'll call it the 50 Ka source. And let me know now if you don't agree with 50 Ka. If you want to do some other value, let me know now, because when we convert the actual, put the impedance value there, that's when it'll matter. So let me know if you don't like the 50 Ka. All right, so the next one is the conductor, and that's going to have a resistance and an impedance. So this will be C1. And then the next one is just going to be an inductance, and this will be T1. T1, C1, source, that'd be the upstream. And then this will be C2. So C1, T1. And then you have the conductor 2, which will be the same as conductor 1. It will be a resistance and an inductance, and this will be C2. And we'll say this is panel board. This is panel A, and this will be panel A. All right. So that is our impedance diagram. We have to convert each of these components into an impedance. So let's work our way down from the equivalent source, the 50 Ka source at the upstream. And if I know my X to R value and my 50 Ka, I can calculate a real and a reactive component thusly. So let's talk about the source. We know it is a 50 Ka at a 6 X to R ratio. Now, I'm going to be using per unit. Now, what we know is I per unit is equal to, we know I actual is equal to I per unit times I base. Now, what is I base? I base, and this is on the 480 volt side of the picture. I base, this is what I'm getting into now is per unit theory. If you're not familiar with per unit, you can look it up. I'm not going to go through to explain per unit. I'll tell you what per unit. We use per unit. Power systems engineers will use per unit to make sure that we can add, what I'm going to do here, I can add impedance values regardless of what side of the transformer that they're on. And then I add them all together because they're percentages basically. And then I convert that back to an actual value by multiplying the per unit times the base via the equation that I'm showing you right here. So I know I base, if from this equation here, I base is equal to I actual, actually, I per unit is equal to I base divided by I actual. Now, I base is going to be the full load amps on the primary of the transformer. So 500 kVA divided by the square root of 3 times 0.48. That is my, and I know I already calculated it, but I am going to calculate it again. 500, 3 square root divide 0.48 divide 601.4, 601.4, 601.4. So I per unit, I'm sorry, not I per unit. Yeah, I per unit is equal to 601.4 divided by 50,000 amps, 50 Ka. That is 601.4, 50, 1, 2, 3, divide 0. And that's actually Z per unit. This is Z per unit. So I'm going to get rid of this. I'd have to derive that, and I'm not going to derive it right now. So it's 0.001 2028. 0.01 2028. Check my math for me. So that's my Z per unit. Now, we know that, let's get rid of this. We know, what do we know? We know that X to R is equal to 6. And we know that we need to get the angle. So theta is equal to inverse tangent of X over R. Because tangent of theta is equal to X over R. Make sense? And what is that? That is this. It's a triangle. This is X, this is R. That is theta. So tangent of theta is equal to X over R. Makes sense? So it's back to Willie Snyder. Happy Math Day. Happy Math Monday. Yes. So based upon was that Pythagorean theorem? Trigonometry. Based on trigonometry, we know that the tangent of theta is equal to X over R. So if I want to know what the angle is, theta, I take theta is equal to the inverse tangent of 6. And let's do the math. 6 inverse tangent, 80.54. 80. I'm going to do 80.538. And I'll tell you why. Whenever you're doing the math, those decimals make a difference. So what I'll do is I'm going to do this by hand, and then I'm going to take this out to about 3 decimals. Sometimes I'll go a little bit further, depends. But I will then I'll put it into an Excel spreadsheet and we'll verify our numbers. All right, so we know that theta is 80.538 degrees. That's our angle. So, and that's going to be important. Why? Because when I want to break, if I want to know the X and the R values, I take Z per unit 0.0120. Ooh. Nope. That's right. All of that is right. I screwed up. I knew there was something I did wrong. All right. Okay, we're going back. We're going back. This is I per unit. All right, so I per unit is 601.4. 601.4. Don't ever take shortcuts. All right, 601.4 divided by 50,000. Divide. That is 0.012028. Now, remember, V is equal to IR. I want that. So V over I is equal to R. So if okay, my Z base I gotta remember this. Hold on. So Z base. If voltage, what's my voltage? My voltage is 480. 480 divided by the square root of 3 gives me my single phase voltage. And then I need to divide that by 0.012028. Let's do some math. I'm going to do some math. Okay. Got to get the numbers right. So what is my 480? 480. 480 divided by square root of 3. 3 square root divide. 480 over square root of 3. Hold on. 500 kVA. I just did that calculation. What was that? 601.4. So the full load amps is 601.4 is my full load amps. Divide that by 50 kA. That gets me my 0.012028. So, makes sense? That makes sense to me. 0.1028. Oops. 50 Ka. I just want to make sure I got the right numbers. $50 Ka, 50 Ka. Let me make sure what is my. Unos momentos, señor. 50. I short circuit over I actual is equal to 1 over Z per unit. So I take I base over that. So that is right. All right. I base over I actual is 0.012028. So that is good. I am good there. 0.01208. So now what I got to do is, I already did that. I've got to convert that over to a real and reactive based upon that cosine 80. So what I do is I do the, this is not I, this is X. X per unit. I'm going to call it Z per unit. Z per unit. So Z real R source is equal to the number 0.012028 times cosine of 80.538. All right. So let's do the math. I do 0.012028 times 80.538, 80.538 cosine. That's 1.64393 times 10 to the negative 1. All right, so that is R source. My X source is equal to 0.012028 times sine of 80.538. Okay. Let's go back and we put 0.012028, 80.538 cosine, no, sine times. That is 1.186,435 times 10 to the negative 2. See, these are very small numbers. All right, so we calculate calculated the R and X for our source circuit. And what I want to do is I want to move all of this up. Remember, these are Z per units. And I don't know if I can. I'm writing too big. So this is source. What I'm going to do is I am going to move that down. Just call this source. Source. Continued. All right, so that is per unit. RPU, XPU. So I've got both of those values. Now what I'm going to end up doing is creating a table. So that is my source. Now let's do conductor 1. conductor 1 was what? Conductor 1 is this. Copy. Paste. All right, so conductor 1 is 2 single conductors. 2, let's just write it down. 2 single conductor 500 MCM copper 125 feet. Felix, please do not tell me I am 1 hour late. I cannot believe it's been a 1 hour. Holy crap. Pythagorean theorem for the win. Thank you. All right, so there is my 2 single conductors. Now here's what we do. We will go to table 9. You didn't miss much, Felix. Jeez, yes, 5 p.m. Eastern. Yes, we've been going for a while now. So we're going to go to table 9, Felix, and we are going to go to... We are going to go to alternating current, resistance, and reactances. All right, expand table. 500, okay. Steel conduit, I'm going to use steel conduit, and I'm going to use steel conduit. So the resistance values are right there. And if I go to 500, it's this bottom number. So R is equal to, how about we do this? Z is equal to, resistance is 0.029 plus J 0.048, 0.048. That is right there. Okay. So my impedance is an R, real plus reactance, and it's basically the triangle. That is X, or that is J, and this is R. And these are ohms per 1,000 foot. So the first thing I've got to do, and I need 2 of them, right? So Z in parallel, I'm going to take 0.0029 divided by 2. 0.0029, 2 divide. This is 0.00145 plus J, 0.024. That is still ohms per 1,000 foot, but I have 2 in parallel because I divided by 2. Pin that header. Wait. You're saying I can pin the header? How? How do I? Oh my gosh! You just taught me something, Mr. Dan. There is a thing up here that says pin header, and now I did not know I could do that. You are the man. So I did 0.0029 and I did 0.048. That is what this is all about. Thank you, Dan. You just taught me something. Look at that. All right. So now what I got to do is I have to look at 125 feet. So now if I do Z ohms, 125 feet, I am going to multiply that by 125 feet. So here's what I'm going to do. I am going to add this in my calculation. I'm going to go to my calculator. Good one. Man. I'm going to go to my calculator. I'm going to do 0.00145, enter, 0.024, and then I'm going to do this complex. I hit the shift and I go to complex. Now that shows me a 0.00145. Now they used the imaginary number. I typically use J, but this calculator uses I, which is perfectly fine. But I represents the imaginary number, so that is your x coordinate. The first number is your R, your resistance. So it's resistance and reactance. They designate the reactance as I. I am going to multiply this by 125 feet and divide by 1,000 feet. 125 times 1,123 divide. So my answer is 0.00018125 plus J 0.003 ohms. All right? So that's my ohms. So that is a real ohmic value. Now I need to calculate the per unit value. And to get per unit equals actual over base. Now I'm on the 480 volt side. So let's first talk about what is Z base. And we're going to talk about Z base. So Z base, Z is equal to V base divided by I base. How do I know that? Because I know V is equal to IR. And if that's what I'm looking for, V over I equals R. So Z base equals V base over I base. So what is V base? V base is, on this case, it is 480 divided by the square root of 3. I base is the full load amps. And the full load amps on the primary side, we just did it up here. Full load amps on the primary is 601.4. 601.4. So 480. 480. 3 square root divide. That gets you to single phase. 601.4 divide. Z base is 0.4608. We good with that? That makes sense? I base is 601. Makes sense? All right. So if this is my Z base, let me know if you guys think I did that. Felix, got Dan, Felix. All right. I want to make sure I have that right. All right, so if that's my Z base, then my Z per unit is equal to my Z ohms at 125 feet divided by Z base. And I'm going to do that via this. Hey, Robert from Omaha in the house. 0.00018125. 0.003 complex. So there's my number in real and reactive components. Divide that by 0.4608. 0.4608 divide. Jeez. So that is 393 times 10 to the negative 6th plus J. 6.51 times 10 to the negative 3. I'm hoping hoping that's right. All right. That is my per unit on my one conductor. For some reason, something doesn't smell right. But that's right. All right. That's C1. T1. T1 is my transformer. What's my transformer? T1 is my 500 kVA, 5.4% impedance. So 5.4% impedance. So T1 is 5.4% Z. I'm going to multiply that by 110% because to get my lowest available fault current, I add the 10%. So 5.4 times 1.1 equals, I think that's 5.4, 1.1 times 5.94. Now, another thing we could do, what is the X to R ratio of a 500 kVA transformer? Good question. Okay, so to determine that, what I typically use, just to show you that there is an X to R ratio, a lot of times what we will do is ignore the resistance. So we don't typically go for a resistance on a transformer, but I'm going to do that. So let's go to the color books. I'm going to go to the red book. I am opening the red book, and I'm going to, red book is this. The recommended practice for electric power distribution for industrial plants. I'm using the 1993 edition. Control F, X to R. I'm just going to poke down through here. I'm looking for a specific table or a graph. I know what it looks like. I don't know what page it's on. It'll look like a little curve. Watch, prove me wrong. It's got to be, oh, there it is, there it is. All right, all right. Look at this. So this little table here comes from C37010, and if you want the latest values, go to the latest edition of the standards. But these are, in MVA. So 0.5 MVA is 500 kVA. So if you look, this is a 0 and this is 10. I'm going to call that around 4. So I'm going to say the X to R ratio. This is typical X to R. This is self-cooled transformer rating in MVA. And I'm going to call this a 4. So if I come back to this, I'm going to say is equal to 4. And we know that to get theta, I take inverse tangent of 4 is equal to 4 inverse tangent 75.96. 75.96 degrees. So that I know that T1R is equal to, I have to divide that by 100. 0.0594 times cosine of 75.96. And that is equal to 0.0594 75.96 cosine times 1.441 times 10 to the negative 2. T1x is equal to 0.0594 times sine 75.96. 0594 75.96 sine times 5.76255 times 10 to the negative dose. All right, so there is my real Tx, T1R, and T1X. There is my real, and there is my imaginary. That's my real and reactive impedance values for that transformer. Hey, Alan Burstein. Welcome, brother, from another mother. All right, so there is T1 transformer, and that's real and reactive components for the transformer 1. So remember, we took the X to R ratio from a reference. We used 4 for this 500 kVA transformer. We took the percent Z multiplied by 1.1. That increases it by 10%. That'll give us the lowest fault current. So there we have that. Now we have conductor 2. Remember, conductor 2 was what? 6. Count them. 6. Copy. Emo boy, I tell you. Paste. So here we had 6 single conductor 500 MCM copper at 10 foot. We know what the impedance is. Let's go back to the impedance. So conductor 2, Z is equal to Z is equal to 0.029 plus J 0.048 ohms per thousand foot. All right, so we know that. Now we have to get this, and we are going to use our calculator. 0.029, 0.048 complex. So that's 0.029. We're going to first divide this by 6. Then we're going to multiply this by 10 foot divided by 1,000. 10 times 1, 1, 2, 3 divide. So we have 48.3 times 10 to the negative 6th plus J 80.0 times 10 to the negative 6th. All right, so that is Z in ohms. Okay, Z in per unit. Now remember, what is our Z base? Z base is equal to, remember, V is equal to IR. So we take voltage for, this is 208 divided by square root of 3. And we divide that by I, which is the full load amps on the secondary. So 500 kVA divided by the square root of 3, divide that by 0.208. And what was that again? 500 square root of 3 divide, 0.208 divide, 1,387.86. 1,387.86 0.86. So that is 208, 3 square root divide. That is 120.0 divided by 1,387.86. 1,387.86 divide. Z base is 8.6528 times 10 to the negative 2. Makes sense? So far, so good. So Z per unit is equal to Z ohms over Z base is equal to, we're going to take, I'm going to store that. I'm going to take, here we go, get the calculator out, 48.3 times 10 to the 6 negative. Enter. 80 times 10 to the 6 negative, complex, oops. There we go. All right, that's good. Yep. And then I'm going to divide that by base, which is recall 1. Enter, which is that 8.652 divide. So that is 558 times 10 to the negative 6th plus J 925 times 10 to the negative 6th. These are small numbers. And I did the 10 feet, right? Yes, I did the 10 feet. Oh boy, I hope this works out. All right, so there's my Z. So that's everything. So let's do my source. Here is my resistance, and let's grab this. You know what I'm gonna do? I'm gonna do this. Boom, 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 boom. Copy. Paste. So I'm gonna make a table. I am going to say item. I'm going to have an R and an X. So source, my R is that. My X is that. And I'm going to delete everything else. And if you remember, we had source, we had a conductor 1, we had a T1, and then a conductor 2. And then we're going to tally them up. So conductor 1, here we go. Copy. Paste. Get my eraser out. Here we go. Get my selector. So this is R. And this is X. Delete everything else. T1. T1 is this. T-Rex. I'm going to copy this. Copy. Paste. All right, so T1. I don't like when it automatically changes back. I don't know how to fix that. Okay, so this is R. And this is x. So let's bring these up that way. And then we have C2, which we just did, which is, I think, this right here. Yep, there is C2. Copy. Paste. And we're going to delete that. All right, so there is our conductors. That's our impedance diagram. We converted the impedance for all of these items into this. So now what we have to do is add these up. So I'm going to add all the R's and I'm going to add all the X's. Here we go. You ready? Let's, I'm just going to throw my calculator up. So 1.64 393 times 10 to the 1 negative. Enter. 393 times 10 to the 6 negative. Plus 1.441 times 10 to the 2 negative. Plus 558 times 10 to the 6 negative. Plus, this comes out to 0.179754. Let's add the x's. Zero this out. 1.186 times 10 to the 2 negative. Enter. 6.51 times 10 to the 3 negative. Plus 5.762, 55 times 10 to the 2 negative. Plus 925 times 10 to the 6 negative. Plus, this is 0.0769248.5. All right. So this is our Z total in per unit. Now, I per unit is equal to 1 over 0.179754 plus J 0.769248.5 is equal to, let's do the calculator, 0.179754, enter, 0.0769248.5, complex 1 over, that is 4.7 plus J 2.01. 4.7 squared. (2.01 squared) plus square root 5.111. I don't like that. What writing tablet and software? eBad, I am using Notability on my iPad, and I'm using my cell phone, and I'm just reflecting it up for my calculator. And the angle is 2.01 divided by 4.7 inverse cosine. No, inverse tangent. That's at 23.15. Cosine of that is 0.91. So I don't need that angle. 5.111. So I short circuit is equal to 5.111 times I base. And I base is equal to 500 divided by the square root of 3 divided by 0.208. 500, 3 square root, divide, 0.208, divide, 1,387.86. 5.111 times, that is 7,093. And I do not like that number. All that work, and I don't think that that is right. All right, so let's do this. I'm going to go back. I am going to call up a spreadsheet that I have. And we're going to do this in my spreadsheet. Where is my spreadsheet? Short circuit currents. All right. Here is my spreadsheet. Boom. All right, so I'm going to come up here. I got 50,000. My X to R I said was 6. So my, I should have 0.001977, 0.011864. What did I get? Point 0.011977. I had 0.0164. What did I do wrong? My I base is 601.4. My Z base, 480 over square root of 3 divided by C6. Divided by C6. Yeah. Did I use the right voltage? What's my Z base? Z base. Uh, 0.4608. 0.4608. Let's just do this. 0.012028. So 08 divide 80.538 cosine times. Yep. I'm close there. 480. C9. Given 0.01977. All right, square root of 3, 0.001977. And I don't have the same numbers. All right, well, I'm going to leave that in there. And then I go 50,000. Then I go to my conductor 1. Conductor 1 is, where's my conductor 1? 0.029. 0.029. And my X is 0.0. My X is 0.048. 0.048. And I had 125 feet. And I had two in parallel. And I got my 500. What's my percent Z? What is my percent Z? 0.003. All right, so 00393, 0.0065. So that number is accurate. I'm accurate there. My T1 is My Z per unit is, what's my X? Oh, 5.4%. 5.4. 5.4. 5.4. I'm going to take equals 5.4 times 1.1. So I'm at 5.94% Z. Now, this got me, I just used reactive on this one. I did not break it down into real and reactive. So that was 0.0594I. My C2, let's do C2. C2, I have conductor 1. I have the same information for C2. Control V. Yeah. 500. My length was 10 foot. My conductors per phase were 6. 0.000558. Yeah, look at that. 0.000558. Look at that. There's my 558 number. And then Control Z, 0.00558. And then there's the 924,556. And there's the 925. So my 925 and my 558. So both of those were done correctly. I got my transformer. All right, transformer. Oh, wait. I overwrote. No, I didn't. Okay, there it is. So there's my conductor. Control C. Control V. 10 feet. 6. I have a separate panel in here, so I am going to do 0 feet. All right, so 0 feet. And the reason I did that, I'm going to delete this. And I'm going to delete that. Whoop, Control Z. So the reason I have that in there is because if I want to separate, if I want to put 2 conductors, if I want to land on a breaker. So if I go to the transformer, 15, I got 500 kVA, not 15. 500 kVA, 480 to 208. My percent impedance. Oh, wait a second. I got it up here. Hold on. All right. I know I did that. There's my 5.94. There's my, this is a 500. And 0.029, 0.048. Control V, 10 foot, 6 in parallel. There we go. All right, so I should have, I added something up wrong. I should have 17,575.67 amps. What's this? 0.5. So those numbers came out right. So my error, 393 is right. 1, 2, 3, 4, 5. So my 393 was right. So my conductor, I added something up wrong. And what the other thing that's different is this. 0.01. Oh, 864. No, that's right. 0.011864. 0.011864. I did my real number wrong. I'm going to go back up to my real. I was close. I screwed up my real number for my source. So let me do that math again. 0.012028. 80.538 cosine times. Yep. So that's what I did wrong. So when I did my my calculation here, this value right there, I calculated that wrong. It should be 1.9773 times 10 to the negative 3. So I've got to take that and copy. Come down here to my table. Paste. Put that there. And this is what happens when you make one little error. That goes there. All right, so that's the R. These numbers all work out correctly. Let's do conductor 1. 393 times 10 to the 6 negative. 0.000393. 0.000393. I am off by 10. That's the other issue I got going on. That number. Let's double check this number right here. So 0.00, I'm going to do my calculation again, 0.00145. Actually, I'm going to go back to the beginning, 0.029, 0.048 complex. So that's my number. Then I have to make this 125 feet. And I have 2 conductors. So I divide that by 2. Ah, look at that. See, there's my issue. See, that's 0.0145. Look at that. I have 0.00145. Transpose the numbers wrong. 0.0145. And that's 0.024. So that's where I screwed that one up. Man, oh day. And then when I multiply that by 125 times 123 divide, this is 0.0018125 plus J 0.003. So there's where I screwed that one up, and then I divide that by 0.4608, 0.4608 divide. That's my base. This should be 3.93 times 10 to the negative 3 plus J 6.51 times 10 to the negative 3. So 3.93 times 10 to the negative 3. 3.93 times 10 to the negative 3. So I just added that back into my C1. So I fixed my C1 number. Let me double check my T1. I believe my T1 is good. C2. Let's double check C2. That should be conductor 2. That's on the secondary of the transformer, 0.029, 558. So this would be 1, 2, 3, 4, 5, 6. 0.000558 and 0.000925. All right, so we're good. Now, if I add these up, I am going to add these back up again, just to make sure we got this right. 1.9773 times 10 to the 3 negative. Enter. 3.93 times 10 to the 3 negative plus 1.441 times 10 to the 2 negative plus 558 times 10 to the 6 negative plus 0.0208753. I'm going to add up the other ones. 1.186435 times 10 to the 2 negative. Enter. 6.51 times 10 to the 3 negative plus 5.76255 times 10 to the 2 negative plus 925 times 10 to the 6 negative plus, that is 0.076922485. All right, now I take that 0.0208753 plus J 0.076922485, and I get complex. I do 1 over, and now I get 3.29 plus J 12.1. All right, so that is I per unit. This looks much better. So now I per unit, remember to get the Z, I square both of those, take the square root. So if I take 3.29 squared, 12.1 squared, add those, square root, that is 12.54. 12.54 times I base, which is 1387.8. I don't know, 8. I'm going to call it 8. 1387.8 times, that is 17,402 amps. I short circuit. All right. So 17,402 amps. 17,402 amps. And I'll tell you, so based upon my spreadsheet, I have 17,575. So I am, and the difference is, if I do 17,575.67 minus, I'm 173 amps difference, and that's probably because of rounding errors. Okay, so now I know, based on my one-line diagram, let's go back to my one-line diagram. So now I know that at this bus right here, I have 17,000, I'm going to use from my spreadsheet, 17,575 I'm going to round down. Worst case is down. So 17,575 amps. I short circuit. All right, so I know I have 17,575 amps. Now, what I need to do now, so that's phase 3. So I determined my one-line diagram. We created the impedance diagram, and we calculated our fault currents, okay? Our fault current at the secondary panel board. To determine the incident energy at that panel board, I need to first calculate I arcing minimum, I arc maximum. And minimum is going to be my worst case. I'm going to reflect, because remember, the incident energy in this secondary panel board is determined by the arcing current at the panel board. So I arc here, But the clearing time, the protecting overcurrent protected device is the 800 amp on the primary. So I need to determine the arcing current on the secondary, reflect it to the primary, and determine my clearing time. So now to determine the arcing currents, okay, 6:41. I started at 5. This is going to be a 2-hour program. So now to determine the arcing currents, there is a Bussmann app. What is the Bussmann app? Bussmann arcing current calculator. I should have it. Oh, you know what else we can do? We can verify our numbers too. That's not the right one. Here it is. Okay, perfect. Now, this is going to calculate our arcing currents for us, maximum and minimum. I'm going to generate it here, and then I'm going to use a spreadsheet of mine, and we're going to compare the numbers. So, gap between, okay, so for a panel board, we use a 25 millimeter gap. VCBB, I'm going to use VCBB. Now the voltage is on the secondary, so I'm at 208 volts, and my fault current we said was 17.57. Calculate. I can't leave this empty. I'm just going to pick a number. I'm going to pick a 1200 amp fuse. Calculate. Calculate. There they are. Look at that. So my maximum is 9.25. My minimum is 7.91. So I am going to do this. Copy. Paste. All right. I'll show you what I'm doing. I am deleting panel A. So we know that I short circuit is equal to 17.57 kiloamps. I arc minimum is equal to 7.91 kiloamps. I arc maximum is 9.25 kiloamps. So now let's do this. I'm going to grab my spreadsheet. I'm going to grab my spreadsheet. I have a spreadsheet. File, open recent. I go here. Oh, calculating incident energy. Right there. Okay. All right, so I have my voltage is 208. Whoop. Jason, can you zoom in on the website? Yeah, Jason, I can. Sorry about that. arc.bussmann.com. It's arc.bussmann.com. So here, Jason. arc.bussmann.com. That's the URL. All right. All right. So let's go back to monitor 1. So here I've got this is going to verify the numbers. I like doing things different ways, just like we caught a math error in two areas, just by doing it two different ways. So my 17.57 is my bolted fault current value, and my arcing current is 9.247 and 7913. So there's the 9.247. I'm looking at this line item right here. 9.247 and 7913. And if you recall, 9.247 rolls up to 9.25, and the other was 7.913. This was 9.247. So I feel good. I have my spreadsheet validates the website, which was 791 and 9.25 with the same parameters. Capiche? We good? All right. So now what has to happen now is I'm going to take this 7913 number and I'm going to reflect it. I'm going to reflect this to the primary. To do that, so I arc minimum. Let me get rid of my Bussmann calculator. My I arc minimum is equal to 7.91 times the secondary voltage, 208, divided by 480. And that is equal to it is equal to 7.91 times 208, 480 divide. That is 3.43 kiloamps. That is my arcing current. So that's my minimum arcing current. So now what I got to do, so my minimum arcing current is, so what this means is for an arcing current at that panel board A of 7,913 amps, the primary 800 amp breaker is going to see 3,430 amps. And that's because of the turns ratio. So now I need to find a time current characteristic curve for an 800 amp breaker. So I do a eaton.com/TCC. So I go to eaton.com/TCC, and I'm going to pick a molded case circuit breaker, time current curves. I'm going to go, I need 800 amps. I need 800 amps. 800. Oh, I can go to the MDL. I would probably, the problem I have with the MDL is I wouldn't be able to fit into certain panel boards. I would probably use an NG breaker. So let's go to the NG. So, NG. I need an 800 amp NG breaker. I don't think we make a thermomagnetic. What I'm doing is I'm just looking at the curves. So no, I don't have a thermomagnetic 800 amp breaker in an N frame. So now I've got to look at the instantaneous 800 amps. Let's find my 800 amps. Oh, look. 800 amps. That's the maintenance mode. I don't want that. I want my instantaneous mode. So I am at where's my hold on. That's not instantaneous. What is this? This is ampere ratings up to 350. Ooh, here we go. NG. No, look at that. That is, that's not what I'm looking for. NG, that's not what I'm looking for. Fixed instantaneous override. That's not what I'm looking for. I need an, okay, so this is an 800 amp trip unit. See what this says right here? 800 amp trip unit, pickup ranges anywhere from 1600 to 64. That's, but it's fixed. That's not what I need. I need, oh, here we go. 800 amp. Well, there it is. 1600 to 6400. So does that mean I can adjust it? Fixed instantaneous. There's that. Fixed instantaneous override is at 14,000 amps. This is the value of an electronic trip unit. I want a thermomagnetic. I don't want an electronic. Let me go back to my trip units again. ND, MDL. Let's go to MD. MDL, MDL, ABDE ion. If it's fixed, don't break it. That's exactly right, Robert. Where's my 800? Oh, wait, here we go. 400 to 800 amps. So here we go. Here's an 800 amp. That's still electronic trip unit. I want thermal mag. I don't think I can get a thermal mag in 800. All right, so here's my 800 amp expanded view in short circuit area with short time adjustments set at minimum. So there's my fixed override. That's around 9,000 or 9,000 amps. Range 50. Where's when adjustable ratings for high fault current levels, fixed instantaneous override. There's my short time pickup. There's my short time delay. So I'm going to go with this guy. My fixed, so this is amperes times 100. So where I get into instantaneous is right here. Is right here. So this fixed instantaneous value is right before the 100. Which, if it's 100 times 100, it's 10,000. So I'm around 9,800 amps. Make sense? Brighten me up there. About 9,800 amps is my... So where would be... Whoops. I'm at 7,000... Oh, wait, no. I reflected. I'm at 3,430 amps. Ow. 3,400. Whoop. Sorry about that. My mouse battery is very low. 3,000. So 3,000. So 30. So 3,430 is somewhere right in here. My clearing time would be around 0.4 seconds. So my clearing time is 0.4 seconds. I don't like that. 3,430 amps. It's 0.4 seconds. So if I go and I do 0.4, my calories is 7,152. Because the 9,247, so 9,247, 9,247 times 208 divided by 480 is 4,000 amps. So 4,000. So at this value, my clearing time at 4,000 amps would be 0.3. So my clearing time here is 0.3. So at the higher arcing current, my incident energy is 6.456. At the lower arcing current, my energy is 7.152. Make sense? I still don't like that. 800 amps, and that's what it is. All right, so that means, so my calories that I would label on here is 7.152 calories. Now, what I'm going to do, so that's my calories at that part in the system. Alan, change that MCCB to a local fuse switch for a transformer protection, then use current limiting fuses. So Alan, yeah, Busman will thank me. So here's what I think I'm going to do, Alan. I'm going to change this up. I'm going to come down. I'm going to come down to a secondary and then a main lug only panel board. So this is what I'm going to do, and this is going to be a 2,000 amp breaker. And this is still an 800 amp breaker. Now, if I take that 800 amp to anything larger, which I can go up to 250%. My incident energy will just go up. So if I move the 2,000 amp breaker, I know that my 17.57, I'm at, let's do this. I'm going to do this. Copy. Paste. So now I have a 2,000 amp breaker. Now I'm wondering if I go to a 2,000 amp breaker, which would be a RD or an RD breaker with an Optum trip unit. If I do that, and I get myself a 2,000 amp breaker, $2,000 amperes. I need to have an instantaneous. I need that to work in the instantaneous region. So my mouse is about to go. So now I'm looking through my R-frame breakers. Looking for instantaneous. Here we go. Instantaneous. That's a 1,600 amp breaker. Here's a 2,000 amp breaker, my fixed instantaneous. So I can go from 2 to 8 times. Now I can, if I adjust my instantaneous on the secondary, I don't have to worry about the primary inrush currents. So that's good. So available instantaneous of 2 to 8 times. If it's at 8 times, so if it's 2 times on a 2,000 amp breaker, that's 4,000 amps. So if this was 4,000 amps, 4,000, 5,000, 6,000, 7,000, I'm at a 0.05, 0.06, 0.07 clearing time. So my clearing time is 0.07 seconds for both of those, 0.07 seconds. So now, if it's 0.07 seconds, I'm going to go back to my spreadsheet. Why isn't monitor 1 working? Hold on, I gotta go to display. Oh, wait. Yeah. Display, monitor 1, iPad. Monitor 1. There it is. All right. Sorry about that. All right. So if I go to monitor 1, if I go here now, I'm going to put the same numbers in, 17.57. My clearing time, there's my 2 values. My clearing time is 0.07 seconds. 0.07. 0.07. My higher incident energy is now 1.5 calories per centimeter squared. 1.5 calories per centimeter squared. All right. So now I am at 1.5 calories per centimeter squared. And I didn't have to put an arc reduction maintenance switch in. I didn't have to so I took it from 7.152 7.2 calories down to 1.5 calories. Let me just make sure that that clearing time is right. 0.01, 02, 3, 4, 5, 6, 0.07. I'm surprised it's that long. That's an Optum trip unit. I like the 1.5 a lot better as well, Jason, but I think I should be able to get it lower. I'm at 7.91. I'm less than the fixed over instantaneous override. That's for sure. I don't believe the 0.07 seconds on the instantaneous. Look at that. That's 0.07 seconds. 5, 6, 7. Let's take a look at what does it say. There's a memory effect that can shorten the long delay. The memory effect comes into play. The instantaneous settings have conventional 100% plus or minus 10% pickup points. For additional curve tolerances, contact Eaton. Total clearing times shown include the response times of the trip unit, the breaker opening, and the quenching of the arcing current. So that I have a feeling it'll go faster than 0.07 seconds, 5, 6, 7, but that's what it is. So what we did, I'm just going to go back and pick up. I'm going to take a look at a different. That's my RD. That's my 2,000 amp breaker. Now, if I did two 1,200 amp panels, which I could, you could do two 1200 amp panels. Let's take a look at the ND. If I did two 1200 amp panels on the secondary, I did two 1200 amp panels on the secondary. There's my 1200s. Now, current in 1000 amp increments. So that's 14,000. Where's my instantaneous? Here's an adjustable instantaneous. Last incremental value is 12 times. So I can do 6 times, 7 times. So if I did 1200 amps, see 1200 amps, 1200, 6 times, that's 7200. So that would work. So this would be 6 times would be 7200. So that would give me a 0.03 clearing time. Let's go 0.03. Let's do a 1757, 0.03. Oh, Control Z. That's 0.07. 17.57, 0.03, 0.03. That would give me a, look at that. That takes it down to 0.6 calories per centimeter squared. Now that's even better. So if I separated that into two 1200 amp panel boards, so if I went back, oh geez, I wasn't even showing my monitor. So what I did there was I separated this into, I added 0.03 seconds, because I was using this breaker at 6 times, and my clearing time was 0.03 seconds. So at 0.03 seconds, now I'm at 0.646 calories per centimeter squared is my highest. And what that did, Jason, was that would be like coming down, going to that, coming off of the secondary, come off of that secondary. Now this is 1200 amps. This is 1200 amps. That is doable as well. And then that would make these be 0.646. And that's because I'm at a smaller overcurrent device there, and I'm more into the instantaneous region. Now, I didn't use a fuse. I could put the fuse in there too, and it'll be even better. But so you have a couple choices. And then go to a main lug only panel board. Well, that's 2000 amps. And then this was 1.5 calories per centimeter squared. And the other one was still 7.152, still less than 8 calories. That's with an 800 amp breaker. Now remember, my maximum was what? Let's go back up to the top. The maximum was a 1200 amp breaker. $1,200 amp would put the instant energy really high. All right, so let's talk about what we did. All right, so what we did was we first determined the single line diagram. We picked the primary and secondary overcurrent protected devices, the primary and secondary conductors. We came up with an 800 amp breaker feeding the 500 kVA transformer. We had, for a conductor, we had on the primary 2 single conductor 500 MCMs at 125 feet. On the secondary, we had 6 single conductor 500 MCM at 10 feet. We calculated the available fault current. Oh no! First, then what we did was we basically created the impedance diagram. We created the impedance diagram by converting each of the components. We took the 50 kA source. The 50 kA source, we converted that over to a 0.012028 Z per unit. And then we broke that down into a real resistance and an X, an R and an X value. Then we took each of the conductors, the conductor 1, we calculated the ohms per 1,000 foot. First we got this from table 9. Then we did our 2 conductors per parallel by dividing them in half. Then we figured the 125 feet instead of 1,000 foot, we had 125 feet. Then we calculated the per unit value by taking the base value of 0.4608, dividing that number by 0.4608, and we got 3.93 times 10 to the negative 3 plus J 6.51 times 10 to the negative 3. For the transformer, we took the 5.4% impedance, multiplied that by 1.1 to get the higher impedance. That was 5.94. We divided that by 100 to get 0.0594 per unit Z. Then we went to IEEE Red Book. We found that the X to R ratio of 4 could be typical for a 500 kVA transformer. We calculated the angle by taking the inverse tangent, got 75.96. Then we broke the percent impedance, that 5.0594 Z, and we broke that into an R and an X by determining the R by taking the Z value per unit times cosine of theta. We determined the X by taking the value, the Z, times sine of theta. Then, and that got us our R and our X for the transformer. Then we had the second conductor. The second conductor is it was the 500 MCM, so we still had the 0.029, 0.048. We converted that to, we divided that by 6, and then we took that to 10 foot instead of 1,000 foot. And then we divided that number by the base value on the secondary, which the base value on the secondary is different than the primary. So we had to take our voltage divided by our full load amps to get our base value. Z base was 8.6528 times 10 to the negative 2. And we divided that and we got 558 times 10 to the negative 6 for the R resistance value, and 925 times 10 to the negative 6 for the X inductance value. So then we created our table and we put all of those together. All of our R's and X's, we added all those up and we got our Z total for the entire circuit, which was 0.0208753 plus J 0.076928485. You take, remember, I per unit is equal to 1 over Z per unit, because 1 is the voltage and we consider it to be 1 per unit. Take that over the total impedance, we get 3.29 plus J 12.1. To get the 12.54, we take the square root of 3.29 squared plus 12.1 squared. That will equal 12.54. That is our I per unit. And then to determine our actual short circuit current at that final point, we take 12.54 times I base, and I base is the full load amps on the secondary of the transformer, and we get 17,402. And what we did was we used 17.57 because that was what I had in my Excel spreadsheet, which does a better job of doing the math for us and taking care of all the decimal points. So that was the value that we used. And then we went to determine the arcing current. We used a web page, arcing, blah, 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 arc.busman.com, and we put the value to determine the arcing current's maximum and minimum on the secondary of the transformer at this panel A. That came up to be the lowest of 7.91 kiloamps. So 7.91 kiloamps. We then had to reflect that to the primary, so we took 7.91 times 208 over 480, and we got 3.43. So the primary 800 amp breaker is going to see 3,430 kiloamps. Then we went to the time current characteristic curve for an 800 amp breaker, and we used a MDL. I'm still going back to that MDL. I want an 800 amp breaker. Where is my 800 amp breaker? 800 amps. What was the full load amps? I think the typical inrush current. Inrush on a 500 kVA transformer. I believe it's around 10 times. Or 12 times. Oh, you know what? I'm going to go to the transformer. Hold on, here we go. Inrush. That's what I'm talking about right there. Inrush. So what we used was 5.4. We used this transformer right down here. This last line, and the inrush current, inrush practical maximum, is around 1,487 amps. So we need to make sure our instantaneous is greater than 1,487 amps. 1,487, and it says actual impedance may vary by plus or minus 7.5%. I went 10%. Could have taken it down a little bit less. So 1,487 amps. So we could plot this, and I don't have my SKM up on my computer. But we could plot that primary breaker, and we went to, I could try to pick an NG, but that's an overkill. NG would be a little bit of an overkill. 800 amp frame. The instantaneous is 14,400 amps. So I'd be in a short time delay at 0.05 seconds. 0.05 seconds. Let's go back to the first one. If I did a 0.05, that's a short time delay. 0.05. 0.05. Same clearing time. I'm in about a 1.07. I'm sorry, 7.93. I'm in around 9.24. Why is that the same? 0.05. Oh, wait, no, there it is. So 1.07, 6.54. So if I can bring it down to 1. So depending upon the overcurrent devices that you pick, you can, now you'll probably spend more money for that specific device because it has more functionality. That's the challenge, is you can add some flexibility and get a short time delay that has a fast acting and get your better clearing times, but you have to strategically pick the right overcurrent protective devices for the job. I would love to have a 0.03 clearing time is what I'd love to have, and that would be the best bet. And then you can change your design a little bit. So what we did, we went and we created that, we reflected the current, we picked the primary overcurrent device, and then we changed the secondary, put that 2,000 amp breaker in on the secondary in its own enclosure. The incident energy was reduced to a very nice value. You could also elect to do two 1,200 amp breakers. I'm not sure what two 1,200 amp breakers would cost as opposed to one 2,000 amp. So, but in any case, all of those are the different design decisions that we can make. Figured I would do the math for us, walk through the per unit method, and see how it went. So that's what we did. Hopefully, Alan, oh boy, that's a hard one. No long time pickup. Oh, not LTPU, the instantaneous pickup. Yes. 2,000 amp breaker with a trip unit and the long time pickup setting at 0.01. Are there any rules of thumb where you can quickly approximate the incident energy if you know the fault current? Wow. Ibad, I am not familiar with any of those rules of thumbs. I have a spreadsheet that I use, as you can tell. It is available on my website. When you register, you can download that spreadsheet and play with it. I think what I'll try to do is get SKM running on my other computer and then model this exact same system in SKM. But that's the best that I can think of. So the other thing we could do, that's all there is to it. That's all I got to say. So hopefully, Ibad and Alan, thanks for joining in, Alan. Change the MCCB to a local fuse switch. Yep. Jason Doty, Robert from Omaha. Johnny, have you ever heard of MVA method? You know what, Johnny? I have, but I just use the per unit method. I like the per unit method. It's something that I can replicate in other software applications. I can put it into an Excel spreadsheet. I can do it by hand as well. But I have heard of the MVA method. Everybody has their way to get there. What writing tablet? I already talked about. Got to run. Willie Snyder. Bye-bye. I am having fun. Yep, that was fun. Alan Bernstein. Then Robert from Omaha. Love the calculator. Yep. And there's Johnny NeGuin. Thank you for joining. Felix. All right, everybody. I'm going to sign off. So hopefully you got something out of our session today. I'll try to streamline this into a shorter video, but I just wanted to walk through. This is the first time that I did it by hand, and I did it with all of you. So, and we did make a couple mistakes in the beginning with our decimal points. Decimal points will get you every time. All right. Thank you. And hopefully we will see you on tomorrow on IAI News Live. So catch me tomorrow on IAI News Live and we'll continue our discussion on elevators. Thanks, everybody. Have a good evening. Sure thing, Abad. Thanks for joining in. Thank you, Felix. It was a great journey and it was great seeing you, my friend. Really enjoyed breaking bread, talking to you down in Colombia. Take care, stay safe, and we'll see all of you tomorrow at 12 o'clock Eastern on IAEI's YouTube channel.